Okay, so last time we mentioned the real space Schrödinger wave function and this Fourier transformed momentum space wave function and quantum particle in a box. Okay, so we will go back to this example today, but then we will study different aspects of this chapter, and also for the sake of the future discussions. So as you'll see last time, so we have this single particle in a box, and we know that inside the box the eigenstates or wave functions is kind of linear combinations of sine and cosine, or e to the ikx or e to the minus ikx. But there is a problem with this free particle Schrödinger wave function. The problem is this is not square integrable, okay, because very easily you see that the square of this wave function, if you integrate over the entire space from plus minus infinity, and is infinity because this is some constant, right? So if you square a magnitude, you take the square of this magnitude of u of x, and you'll get simply just a squared plus b squared plus a times b, and so on. So these are just constants, right? And if you take the integral over the entire space of this constant, you immediately run into trouble because this is infinity. So this is not square integrable. But what can we do? What can we do about this? Well, the textbooks tells us there are three ways out of this trouble. I'm not going to provide you with details, but we'll just list the final solution. So the first is actually to consider a very large box where this little a, or the width of the well goes to infinity, so that you could actually normalize this with the finite width of the box. But this is not a good solution, because at the end of the day, as long as a is actually finite but large, and everything depends on this length scale a, and when a goes to infinity, then your eigenenergy goes to 0. Something like a square 2m 2 pi n h bar over a square, and if a goes to infinity, then this eigenenergy vanishes. So this is not what you would like. Okay, so the second solution is that you know that realistic quantum particles, there's always a wave packet, right, associated with this quantum particle. So you would like to use a wave packet formulations to actually give some realistic distributions of your wave functions. And instead of single plane wave like solutions, you consider a wave packet where the wave packet has finite width, and everything depends on this width, and so that you may be able to solve this problem, because in a wave packet formulation, a quantum particle is actually confined within such a width of the wave packet, so it cannot be simply just a free particle wave, and then you could actually find this particle anywhere. So you should find this localized somewhere in the wave packet formulation. Okay, but again, this is not realistic, because this wave packet is really complicated. It's a complicated function of this x, and depends on how you actually describe the wave packet. It may depend on different shape of the wave packet that you impose to the quantum particle. So, but we know that these things cannot mess up with your eigenstate, eigenenergy, and eigenfunction, and so on. So, we just simply do not consider the first two options are practical options. So the final solution is the more practical solution. We know that for a plane wave like this, we actually find this particle is actually proportional to 1 over a, where a is the width of your potential well. And when a goes to infinity, which means that the probability of finding this particle is almost 0, okay, because you get the whole universe that the particle can travel to. So if you really like to ask this question, what is the probability of finding this particle? If the particle is actually a plane wave like free particle, then the answer is that the probability of finding this particle is almost 0. So this is actually the wrong direction to ask, because the particle is not confined in space, but we know very well that this, when the particle actually goes through any volume, surely there is a flux, right? So no matter how unlikely that you find the particle in any place of this infinite white box, so you can always actually imagine that you have some cylinder and the particle actually can pass through the cylinder with the area and some length, and you can actually collect the flux or the probability current of this free particle, because this is something that you can do. Okay, so of course I don't know where this particle is, but I can simply just wait and count the particle number. And so the way out of this trouble that this eigenfunction is not square integrable is that we don't ask this question, that what is the probability of finding this particle. Instead, we should ask this question, so what is the probability current or the flux? Remember, we defined this flux some time ago, right? Okay, so this flux is defined as the particle number that you catch per unit area per unit time. Okay, so no matter how hard I find this particle, but it should always pass through some area, right, or volume, which you can collect. And we can also calculate this current flux or probability current or flux of this free particle by evaluating this quantity here. So of course you get finite value. So let's just look at a particular example of such a free particle. Suppose that there is a particle described by this wave function. By the way, let me just define this flux. Flux in the classical fluid dynamics, it is given by the velocity of your fluid times the density of your fluid. Okay, for a one-dimensional problem, so this is simply just velocity, and is actually the number of particles per unit length. Okay, so this is something that you can calculate. So let's just do it. If you have this plane wave traveling from the left to the right, like this, and you can actually calculate this flux, which I call this J plus, because this travel from left to the right, actually to the positive axis, positive x-axis. So I call this J plus, which is what, if I call this just C as a prefactor, and this is simply just C squared over m times p. Right, so if you simply just take the differentiation of psi with respect to x and also psi star dx, and then you subtract this from that term and you divide it by 2im, and you immediately get this c squared divided by m times p. Well, this is simply just p over m times c squared. What is p over m? P is your momentum and m is your mass, and momentum divided by mass is nothing but velocity, right? And as a result, now what is the interpretation of a C square? C square should be interpreted as the number density. C square density of your particle per unit length. And we know very well that this prefactor 1 over square root of 2 pi h bar is actually a normalization factor. If you want to normalize this momentum eigenfunction of a momentum operator, psi of x, and this tells us that this density of the particle per unit length is given by 1 over 2 pi h bar in this simple free particle moving to the right. And you can also calculate psi, that is plus and minus. So suppose I have another plane wave moving along the opposite direction from the right to the left, namely towards the negative x-axis. Then we can actually calculate this j minus. So if you simply just plug in this psi minus wave function back to this flux formula, and you'll get almost the same except the sign, which is minus c squared p over m. So the reason why you get a minus sign is because of this minus exponent appearing in this wave function. So if you take the derivative of this e to the minus ipx over h bar, you get a minus p, right, instead of plus p. So we could very easily interpret this j minus and j plus in the sense that for this particle moving to the right, you have a positive flux, and for the other particle moving to the left with the same velocity momentum, and you get a minus flux. And therefore, we can very easily detect and compute the plane wave, a free particle moving in space, which is not confined in space, but we could calculate the flux associated with that simple plane wave moving particle. And later we will take advantage of this flux and to analyze this one-dimensional potential problem, that particle can actually penetrate through this barrier, potential barrier, and then it could also get reflected, and we could calculate those flux, at the interface of this potential profile, and the flux should be conserved. And based on this flux conservation, we are able to find out all this simple one-dimensional potential problem. So the lesson we learned is that the flux is really a good quantity to compute, and the flux should be conserved. Okay, so this is the lesson we learned based on this normalization problem of the free particle. Even though this free particle is not square integrable, but we can still measure and detect and calculate those free particles by their flux. And this is something that we will do in the following chapter. We will discuss another important concept, which is degeneracy and parity symmetry. By the way, this is the easiest calculation you can do, but you need to do that by yourself. You simply just plug in this wave function back to this current flux formula, and you should convince yourself that this is given by the results shown here. So let's talk about a very important concept called degeneracy. So in quantum mechanics, oftentimes we find more than one states. There are different states, but they correspond to the same eigenenergy. Okay, so if you have more than one independent eigenfunctions which corresponds to the same energy, and we call these eigenfunctions degenerate eigenfunctions. So take a very simple example that we just mentioned. Suppose we have two free particles say moving to the right, I call this psi 1, and moving to the left, e to the minus ikx, I call this psi 2, and both eigenfunctions are independent because if you take the overlap integral, which we can define already, and this overlap integral vanishes because by definition this overlap between psi 1 and psi 2 is defined by this integral where this psi 1 you get star and psi 2 no star. Yeah, either way. So then this e to the minus ikx with a star, which is e to the plus ikx times e to the ikx, you get this e to the 2 ikx. So this vanishes because this is oscillatory function, right? It's oscillate in space. So the positive and the negative value of this e to the 2 ikx cancels exactly. And so you get 0, which means that these two eigenstates are degenerate and they correspond to the same energy because E1 is the same as E2, which is this value, right? And so these two functions are eigenstates of a free particle or free Hamiltonian where you have only kinetic energy, and both plus and minus free propagating wave gives you the same kinetic energy. Okay? But these two wave functions are certainly orthogonal to each other, so which means that this psi 1 and psi 2 are actually independent eigenfunctions. And so by definition, in this case, we have a degeneracy. So the degeneracy actually tells you that either the particle moving to the right or to the left, they have the same energy. But how can we distinguish these two degenerate states? We could very easily see this difference, right? So psi 1 travels to the right, but the psi 2 travels to the left. So the difference lies in the momentum, k or h bar k. One is positive value, another is negative value. So to distinguish these two degenerate states, we could very easily use this momentum operator. So if I simply just apply this momentum operator onto this free particle, e to the plus minus ikx, and I immediately get this plus minus h bar k e to the I plus minus kx. Because this momentum operator minus I h bar d by dx, right? Okay, so you take a differentiation. It's plus, you get the plus, minus, you get the minus, and I times minus I is actually 1, so you get plus minus h bar k. So in other words, we could distinguish these two degenerate states by measuring their momentum, right? So you could take a measurement of the momentum by this operation here. So you measure the momentum of such states. Of course, this tells you that momentum e to the plus minus I k x states are also eigenstates of momentum operator, right? Because if I apply this momentum operator onto the states, I get this eigenvalue plus minus h bar k times the same states. So this satisfies the eigenvalue equation. As a result, this states e to the plus minus ikx are eigenstates of momentum operator. So to distinguish this, you need to apply the operator. This degenerate states are also eigenstates of that operator, so that you could distinguish these two. So another way to distinguish these two, of course, you could use the different examples. Suppose my psi 1 is actually cosine kx, and psi 2 the sine kx. And we know very well that these two could be eigenstates of some particle in the box. And we know very well that these two states are orthogonal because cosine is an even function of x, but sine is an odd function. So even odd functions are, of course, independent from each other. And of course, these two give you the same energy, just like this two traveling waves from the left to the right or to the left. Here, cosine and sine could be different examples of degenerate states. So these two states are independent states, but they have the same energy. So we could call them degenerate states. So how could we distinguish these two? Well, of course, I already told you the answer, because cosine kx is the even function of x, and sine is the odd function of x. So obviously, the even odd properties of this function could distinguish the two. But what is the operator corresponding to this even odd nature of the wave function, right? So this is called parity. So parity is a very important symmetry in physics, especially in quantum mechanics. So we will introduce formally this operator. Suppose I apply this parity operator onto any eigenfunctions u of x, and what I get is you simply just take a mirror symmetry by taking x to minus x. This is a mirror reflection operation. And suppose I take the parity operation onto this cosine kx, what I get is a cosine kx with a minus sign, cosine minus kx. But we know that this cosine minus kx is the same as cosine kx. But what if I take the parity operation onto the sine function? Well, I get minus sine kx. Yes? So in other words, the even parity and odd parity should actually behave in the opposite way, right? But both cosine and sine eigenfunctions of parity. Because, as I mentioned, this operator acting on this cosine gives you +1 as an eigenvalue times itself, right? So it satisfies the eigenvalue equation. And likewise, if I apply the parity onto the sine kx, I get -1 as an eigenvalue times the sine kx itself. So both states satisfy this eigenvalue equation. So both cosine and sine kx functions are eigenfunctions of parity operator. Okay, so here comes a non-trivial statement that in order to distinguish these two degenerate states, we need to apply an operator. But these degenerate states are eigenstates of that operator. For example, this momentum operator or the parity operator. So we will come back to this in just a moment. But here, we simply just illustrate these two important concepts. One is degenerate states. Another is the so-called simultaneous eigenstates. So let me just use more formal definition. So this e to the plus minus ikx is actually simultaneous eigenstates of momentum operator and your free particle Hamiltonian. And here, cosine and sine function, again, are simultaneous eigenstates of the parity operator and your Hamiltonian. Okay, so here comes a very important concept in quantum mechanics, namely simultaneous eigenstate. Okay, so simultaneous eigenstate tells you that this eigenstate is the eigenstate of the momentum operator and Hamiltonian. In other words, you could write down this eigenvalue equation for both operators acting on the same eigenstate. You get maybe different eigenvalues, but both operators could satisfy these eigenvalue equations. And likewise, the sine and cosine functions are simultaneous eigenstates of parity and Hamiltonian. So, of course, these two combinations are eigenstates of some free particle Hamiltonians inside the box. But then these two functions are also the eigenfunctions of parity. So, therefore, these combinations are simultaneous eigenstates of parity and Hamiltonian. So, we will study a theorem if we have a simultaneous eigenstate of any two operators and we have some relations between these two operators. Okay, so let's just look at this consequence of this parity symmetry. So this is just example we just studied, this single particle in the box. So if we move our origin to the center of the well of the box, then we get this even odd symmetry eigenfunctions, as we already mentioned. For n equals to 1, 3, 5, the odd number of n, you get the cosine function, which is an even function. For n being even, you get odd function sine. Even odd functions are eigenfunctions of parity, as I mentioned. But if you use this psi e or psi o represents this even odd solutions of this psi, then you can immediately see that parity operator acting on this even plus 1 psi even, but acting on this odd eigenfunction gives you minus 1 psi odd. So we call this eigenvalues lambda plus and lambda minus. And as I mentioned, these two eigenfunctions are simultaneous eigenstates of parity and Hamiltonian. So inside the box, we have simply just kinetic energy. There's no potential energy. Of course, H Hamiltonian operator acting on this psi even if you and eigenenergy and even times psi even, and odd if you odd. So both psi even and psi odd are eigenfunctions of Hamiltonian inside the box, and therefore, psi even psi odd are simultaneous eigenstates of H and P parity. So we will come back to this just a moment. Let's just consider any function, any Schrödinger wave functions. I could define the even and odd combinations of these functions. So psi even is simply just 1/2 of psi of x plus psi minus x, and psi odd 1/2 of psi of x minus psi of minus x. Right? So any arbitrary wave functions could be decomposed in terms of an even part of the function and odd parity part of the function. Right? So you simply just add these two, you get back to this psi of x, but psi of x could be decomposed in terms of an even symmetry component, an odd symmetry component. And so if you just rewrite this even component, you get 1 plus parity operator acting on psi of x, which I call this psi plus. For the odd, we get 1/2 1 minus parity operator acting on psi of x, which I call this psi minus. This is just a notation, right? So this is just saying that this psi minus x could be rewritten in terms of parity operator acting on psi of x. Here comes non-trivial statement. So we would like to ask the following questions. Under what conditions and even or odd eigenfunctions will remain even and odd all the time? So we know this even odd function, right? But we need to figure out the conditions under which the even eigenfunctions still remain even, odd functions still remain odd. But this is a bit trivial because in this particle in the box, once we have formulated this cosine and sine as their eigenfunctions, and they don't mix up. So cosine cannot be sine, sine cannot be cosine. So it's clear. But in general, I would like to formulate the condition under which even eigenfunctions will remain even all the time. I mean, if you time involve the Schrödinger states, and this even eigenstates cannot be time involved into the odd eigenfunction, vice versa. So we will figure out the condition to satisfy these properties. And the condition is that the commutator between the parity operator and Hamiltonian commutes. See you on Wednesday.